All right. Good morning, everybody. Let's get this started with a sip of coffee first. All right. Today's topic continue where we left off last week, which was liveness analysis. Um, we did fine. We built a liveness analysis that analyzes our intermediate representation, and it builds live in and live out sets. And today I want to continue where we stopped, because now with the live in sets we have everything we need to continue to implement this paper, which implements a linear scan register allocation algorithm for an IR that is in SSA form, which is exactly what we have. And it also includes register constraints, which is interesting if you have what I'm doing, a mid code for x86, where you have to make sure that some stuff is in certain registers and constraints. So what this algorithm requires is that we prepare the IR, what we have, in a certain way, right? We need to generate moves for the phi operands or phi instructions. We need to number the instructions. That should be relatively easy. And we need to compute the live intervals. The live intervals is what led us down the path of implementing liveness analysis last week in order to have this little thing here, which is the live in set for each block. So now that we have this, we can actually, implement this section here, which is preparing the IR for linear scan. I made some rough notes, which you can see over here, which is my normal notes for implementing this kind of stuff. So I took this algorithm here, gen moves, which it doesn't even fit on one line, and turned it into pseudocode, JavaScripty, whatever, for ease of reading. And this is what we're going to implement today. And since I have no idea yet how this generating moves for phi operands will be used in conjunction with SSA deconstruction, which is what I already implemented in a compiler, or let's see the middle part. So we deconstruct SSA, which also inserts move instructions into the IR, because you remove the phi functions, these ones here, right? And you insert moves up here. The thing is, though, that in SSA deconstructions, you move these operands into the same thing, which means into the same register, which means the resulting IR is not in SSA form. So what I'm wondering is, after we have this and I run this through this deconstruct and this remove phi function pass, then I suspect we would end up with duplicate move instructions here, which would move, I into I7 and I5 into I7 and I6 into I7, and then this would be removed, I think. So we would have duplicate moves, and then the question is, do we need an optimization phase pass that removes these again? So I'm saying all of this to conclude with, I'm not going to worry about this for now, because I want to implement this, and then we see how far we can get. Because I have a suspicion, after having read the paper, that what it does in section 4.4, which actually assigns registers and joins registers for different instructions, then we probably can simply remove the phi functions, because instead of having virtual registers, each instruction now has a real, an x86 register, and we wouldn't have to worry about virtual registers anymore. That's my working thesis right now, but since I have a really short attention span and a really small CPU cache in my head, I'm just going to worry about the next step, and that is implementing this. So what we are doing, or will do, is we're gonna create a completely new file that looks kind of like this, which we just, we're just gonna straight up copy this, and we call it regalloc, right? And then we say generate moves for phi operands. All right, and then remove this. Say generate moves for phi operands. And this does nothing. We're just gonna put some stuff in here. It just prints stuff, and it removes the warnings. So this file is not included in the module tree, which is why we don't see any warnings yet or diagnostics yet that this is wrong. But we're just gonna ignore this for a second and just type out some stuff so we have something work for. So this is nasty copy and pasting of me. But what I want is I want a new separate playing ground that doesn't, it's separate from the rest of the code base, and we can see what is actually happening when we implement this. So we call this basic CFG with 5 functions, which is what we also had last time. And then we have this, and we run it through analyze, which is the macro we just defined up top. And we can already make an assertion. So we could make this our example. But let's remove this. So we could already add assertions to this, but we won't for now because we need to set up this file. You know what? Let's make a false assertion here. Assert equal, and let's say B2. Wait a second. B2 is FB2 instructions len. Do we have a not EQ? Is that a thing in Rust? So this is kind of what we want, I think. We want to move operations inserted into B1 and B2, so whatever. Okay, so this doesn't run because we need to go into middle, and we need to say after liveness analysis, we're going to do regalloc analyze. And somewhere here, we say mod regalloc. Oops. And now, see here at the bottom, we get the errors and the warnings and the hints, which means diagnostics are back again. And we can jump into our thing, and it says fail to resolve use of undeclared, blah, blah, blah. So we say use create middle liveness. Unresolved macro. So okay, assert not equal does not exist in Rust. And this is of course. This doesn't make sense. Borrowed value. Okay, we can always clean this up later. And say alt len. All right, so now we can clean this up. Unused import hash set, because we don't have a hash set. We don't use the. Wait a second, can I use a code action for this? Unmerge use. No. What here? Remove the unused imports. Boom. There you go. Thank you. NeoVim LSP implementation. All right, so we only have one unused variable, and that is context, which I am not sure we actually need. Let's see. All right. So now now we got this set up, which is our basic thing to set up a test case, and we have a function that is generating moves for phi operands, that should generate moves for phi operands. let's see if we can make this close enough to this other example, right? Let's watch me. It worked. All right. So now, well, that's not nice, right? But we get what it is. So we say a equals 11, and then we say a equals b plus 1, which is in SSA form should create a1. And then we say c equals, let's say a plus 5. This is just a use. It doesn't matter if it's in a binary instructions or not. So what we do now is we make sure that our CFG here is actually what we just drew in this comment. So B0 has one instruction back here, which is a move, which moves 11 into A. Now let's go to B1. We have a move 22 into B. Then we have a move that adds B and 1 and moves it into a temp because the IR generator will always move stuff into temp registers, which is something that could be optimized, but it's not yet. So this, if this was in the original source code and we would turn it into IR, this would look like a move from, a binary operation, moving something into temp and then moving the temp into the final destination. So why is the syntax highlighting so weird? There you go. So moving temp1 into A. Then this is B1. Now let's rename this one and say B2. Which makes this wrong. Now we say the old len B1 in slen or old len, and we say B1 instructions len B1 ins old len assert. Is there really no assert? Aha. NE. There you go. They should not be the same. So we got B1. And now we need B2. And B2 again has two instructions. A plus 5 into temp. And then temp2 into C. All right, so then we can remove B3 completely because we don't have a B3. B3 doesn't exist, B3 doesn't exist, we can remove this. E doesn't exist, temp3 doesn't exist, remove it. So now we need to make sure that we wire these blocks up correctly. So you can see here, I have these helpers, terminate if, or what did I just delete? I think it's called terminate goto. So we need to terminate B0 and say if, it doesn't matter what the condition is, we just put it true in here. The important bit is that this block B0 has, two pointers to two other blocks, to two successors, which is what this helper does. It wires them up and says, give this block a terminator and then connect the blocks setting successor and predecessor pointers. So we need to terminate B0 and say on the left side, it goes to B1, and on the right side, it goes to B2, right? And then we need to terminate B1 and say terminate go to FB1 to go to B2. Terminate go to, well, there you go. Terminate go to. Because this block, or this block here is now pointing to this block and this block, but this block also needs this pointer here and point to B2. All right. Okay, so we got this wired up. This looks pretty similar, right? So what I want to show you now is, let me make this a bit smaller by paper. Actually, we can move you up here, paper. I'm not sure. Yeah, we might need you. All right, so paper, we're gonna keep you over there. So now what I want to show you is we analyze, we do this macro, we do all of the stuff needed for SSA, we do the dominance analysis, we do insert file functions, rename variables. Actually, what we can do is, let me check. We can just do this, I think. Oh, this requires a CFG. But then, yeah, we could do this. We could say let mute CFG, CFG new, CFG insert, func ID, func, I think, and then we can say SSA. No, that doesn't work, because then the func would be owned by the CFG data structure, and we would get a borrow checker screaming and say, yeah, you can't do this. All right, so this is, let me make a mental note here. So I say mental note and then I write it down. So remove duplication here and make sure we don't forget to. Okay, because this is something I'm scared of in general with this compiler, that this is the middle end of the compiler, and it does this. It calls name resolution, then it runs a type checker, then it builds the CFG, then it passes the CFG into another pass called string lowering, where we remove string literals and replace them with references to the data segment. Then we turn it into SSA form. Then we do liveness analysis. Then we now hopefully do register allocation. And then we do deconstruct, and then it goes into code gen. And the problem with this, and what I'm scared of, is this all needs to happen in that order. If you run this without having done dominance analysis, it will produce garbage output, or it will crash at some point. Crash would be nice. Garbage output is what I'm scared of. What I'm really scared of, that I build something and then I assume all the tests passed, this looks nice, I built this, great, and then I realize, oh, actually I forgot to insert file functions, so this is why it passes, because I didn't pay attention to that. So yeah, I love the note. We should make sure that we don't do this. So coming back to what I wanted to show you, here we analyze the function, right? And let's print this function. This should now be an SSA. It should have run through our new function. And if we run this test, you will see that this is, it's printed twice. Let me remove. Well, actually, you know what? We can remove this because our function up there already prints it. So our dummy function here only prints the block ID and the block itself, and the block the blocks, they implement the format display trait. So this is why they looks that nice. So what I want to show you is this is the input, which looks roughly like this stuff over here in the paper. And this is the IR that we generated, right? Which should look like this, right? So of course, this is a detail. This is referring to this. It just means there could be other instructions, so we don't have this. But up here, we have the move of 22 into A. A is 2000, right? Okay, that is already wrong. Why is that B? Why is 22? Okay. This is live. This happens. I looked at the wrong thing. So this is the block. We move 11 into A. All right. This is this block up here. And then we say if true, go to block 1, which is this block, and block 1 we have move 22 into B, which is 2000. Then, and here's where it gets interesting, we say B plus 1, move that into a temp register, which is temp 1 here, temp 1, register 6000. And now we would move the result of this operation into A and override A, but we are in SSA form, static single assignment, which means you never override a value. You always write to a new value, right? I'm not sure that this is the most or best or succinct explanation of SSA, but it means you cannot write into the same value twice or multiple times. You always write to a new name, which means in SSA, you give them versions. So here, when we say A equals B plus 1, then we, this is the result of A plus 1, B plus 1, and then we take that result and move it into 1000 underscore 1, which means it is not the same register as the one we wrote to in the first block. It's the new version. So this is SSA for you, right? It's the same. We know that it's the same name, but we just give it a different thing, which makes liveness analysis and what we did last week much easier, because now every value has a different name. And then in the last block, A, this is a bug, is it not? We have a file instruction without operands. And then, oh yeah, I know why we have a bug. Okay, so we're missing the operands here, and that is exactly what I just said. I'm scared of garbage output because things need to be set up the right way. So this phi function is missing operands. It should actually have this. It should say, I7 is either I4, which is A0, 1001 or 1000, but we don't have any operands. And the reason is because of all of this garbage over here, where we need to, where we need to set up the assignments by hand. Okay, so if we would write this other test, if we would write this test here, like our CodeGen tests, and where are the tests? And we would say, hey, here's a bit of code, compile and run it, and then what this test does, this is CodeGen, so this is the last thing. What this does is it actually parses it and runs the whole middle stage of the compiler. And then nothing is missing because everything comes out as it is, in the compiler. But since we want to test the middle part of the middle end, we don't run the whole middle stage, which is why we have this thing up here, and which is also why we don't build the IR and build these by hand, because it's easier to analyze them and have IDs. But, the problem is that we also need to set up the IR correctly, and this here is wrong. We need to say in which block does each variable get assigned, or have a move operation where the variable is a target. So this we didn't update. So here's a bet. I'm sure if we fix this and I rerun the test, we will see that the phi function now has operands. Okay. So add assignment. A is assigned in B0 and in B1. B is assigned only in B1. C is assigned only in B2. D is never assigned. Temp1, now we can remove D. Temp1 is assigned in B1. Temp2 is assigned in B2. All right, let's run this. There we go. I won the bet. Now our phi function has the correct operands. So let's compare this. So the phi function here says, hey, when we arrive in this block, A, this one here, this A, it could be either I4 or it could be I1, depending on which branch we take. Okay, this is what phi functions do. They say this value depends on where we come from. If we come from this direction, then it's this one. If we come from that direction, it's this one. So our phi function here in block 2, which is this block, says, hey, A 1001, which is now another version, right? And this other one got bumped because it's not working correctly. 1001, so the new A, it could either be 1000 or 1002, depending on whether you come from block 0 or you come from block 1, right? And then we have this value in this register, and we add 5 to it, which is what we do up here. And then we move it into a temp, and then we move it into C. Okay, so this looks correct. Our test is failing because the instruction length of B1 is still the same. We didn't insert any move instructions. So far, so good. Let me just pause it for a second and drink something and check chat before we get started with the actual coding and fixing of this test. All right. Let's do this. We have this set up exactly as in the paper. What we want is we want this edge, this line in the graph, to be split and have a new block inserted, right? The algorithm says if the number of predecessors of, for all predecessors of B, so you go through all B's, and then say we're at this B down here, and we say if the number of predecessors is more than 1, which is the case for this block, and the number of successors of the P for all predecessors of then insert a new block between P and B. So it says, hey, this block down here, or let's take it over here. B2 has more than one predecessor. It has this predecessor, B1, and it has B0. And then if we look at P as a predecessor, we say, hey, you have more than one successor because you have B1 and B2. Then we insert a new block in here. And then for each phi function of B, do this. All right, let's do this. So let's pull up my notes real quick, and we take this pseudocode, and then we do the same thing as we did last week, and we just insert the pseudocode up here, and then we turn it into code. The interesting thing is, as I said before, I'm sure that this is similar to what we actually do for SSA deconstruction. Let me show you. So what we do in SSA deconstruction, remove phi functions. See, we say we split edges. But how do we do this? We say we go through all the blocks, then we look at all the phi functions, which is what we do here. Right, for all predecessors of P. So we do the same thing here. We walk through all the phi functions. And, you know, going through each phi function in a block and then looking at the operands, which is what we do here, is actually looking at the predecessors, because each operand of a phi function, as we saw in our test output, each operand of a phi function is this. It includes the ID of a predecessor, right? So this is why I think this looks similar. Our new pseudocode algorithm here says for all predecessors of P, like we iterate over them, and then for each phi function of B, and then take this operand corresponding to P, blah, blah, blah. So we could flip this around and we say for each phi function, you know, instead of saying for each predecessor of P and then for each phi function of phi of B, we could say for each phi function of B, for each operand of phi, and then, you know, each operand has a predecessor name. But I'm not the smartest person, so I'm feeling a bit cautious about deviating before I even wrote something down. So let's take this from the top. Let's take this from the top. Split edges. This is the same. So split edges, okay. Yeah. All right, okay. So we go over each block, okay? And then we say for P in func predecessors ID, and we say pred ID, right? How does this work? It says give me this and then iter over it. So let's do the stupid thing. We say predecessor IDs equals self predecessors get ID, and we say func. You know what? Let's just clone this. It's a hash set, and then we say consider giving copy. Let's remove this for now. These are all the predecessors of this block, and then we say for pred ID in predecessor IDs, let pred successors equals func successors get pred ID unwrap len change this to pred ID. And then we say if this is interesting. If predecessor IDs len, I'm here, bigger greater than 0, greater than 1, and numpred successors is greater than 1, then we need to insert a new block. And we say let block equals, we say block, I'm just typing stupid stuff here, block to get moves, or I block, which is what it's called up here. No, it's called N. Yeah, it's called N block, the new block, and we say it's an option block ID, and it's none. And then we say if the predecessor ID bigger, then we're going to insert a new block, which we're gonna copy. That's interesting. Okay. Oh boy. Block ID counter. Where did we get this from? You get this from the context. All right, then we say n block replace context block ID counter. How do we use the block ID counter? All right, just this. New block ID. Context block ID counter is this. We say and replace new block ID. Close this. Cannot find function. Import this. End block. We're gonna make this mutable. Yep. Yeah. Otherwise, else new end block replace with pred ID. Yep. We're gonna dereference this. All right. So this should be this. We go through all the predecessors, which is this, for all predecessors P of B. And then we, load, we want to insert a new block N between P and B, or N is equals P. So we want to find out in which block do we have to insert the move instructions. And if the block, like this, has multiple predecessors, we need to split the edge and insert a new block in here. And I'm not sure whether I can use my existing logic, but I think I might be able to. Then we insert a new block, and, say this is the block. The problem then, of course, is this. Because we need to insert hey Connie, I appreciate it. The problem is then inserting the instructions. You know what? But we can do this. Yeah. Okay. So let me type something. I got something in my head. So now we say, let's copy this from SSA again. Give me all the phi and operands. Plug instructions, iter, yeah, we comment this out. So now we're doing this. Give me all the phi functions. Then we do this. For op in phi operands, we create a new move instruction. But here, you know, it's the same thing, but it's man, I feel like it's the same thing except we don't remove the phi functions in this algorithm because we replace the operand of the phi functions. Yeah. Okay, so let's do this. How do I block people? Is this possible? Ban? Is it banning? Block, there you go. Yeah, blocked. All right, thank you. Blocked. I'm losing track. Let's just type this. Okay, let's do. Sorry, I've said this 3 times now, but let's just really do this stupid thing without worrying about whether it's the same. So okay. Aha, this is also different. Is it? So what's the target of these new copy instructions? Oh, interesting. Okay, so +1. That's wrong. Okay, so for each phi function of B, we create a new reg move, but we need to find out the operand corresponding to P. So let's just, this is loops and loops and loops. This is super inefficient, but we say if op, and then a var, it's a var, and a var has, I think, a block, yep. If block does not equal pred ID, then we can continue and skip it. Yep, I think that might be it. Then we just ignore it. And then we need to say the phi operand. So then we move. This is correct. We move this. but we need to move it into a new number. So we need to bump the number of this. Print L. So we generate a new move instructions, right? And we want to say, hey, into this block here, this block, we want to insert a move that moves this, which is the operand of this phi instruction, I4, that corresponds to this block, right? Because the block is the same as the predecessor. We want to create a new move instruction and move it into this. But the target of this move instruction needs to be the same name. It needs to be A3 or A5 or A4 or something. So how do we do this? How do we increment the versions? Renamer, we have the renamer. What the, aha, self inc and get new versions, see? Yeah, we got the renamer, that's cool. All right, let's use this renamer then. Oh, it's not public. Why does pub? Something is broken here, SSA. Do I also need to make this pub? Let's restart this for a second. Reg alloc. Import, now it works. Okay, so now we say renamer, rename, op place. Does this work? That would be amazing. That would be amazing. Okay. So now we have this copy. And then we ignore the to do join I with phi. We ignore this. The problem is we need to say we need to override the operand and say phi operands, this is a var. We need to say the place is now a different place. And we say op1 equals new target. And now I need this to be mutable. I don't. It just copies the calls ops to vec. All right. Okay, what is ops? Okay. Let me say copy instructions, insert, n block. Wait a second, let's also copy this from the SSA code. Oops. Copy instructions. Yep, this is what we need. Entry, n block, unwrap. And then we insert this. Yep, and then we need to do this. Aha, there you go. This work? I'm not sure. I'm sure this is just, this will not work, but let's see. Let's, you know what? Let's run the tests and say print before. And then we say after. And we run this. It passed. All right, watch this, watch this. Okay, so before blah, 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 we have, aha, this is, okay. Let's take this out. Nope. Okay, before we have in block 2, we have these phi's. And now, oh boy. All right. So now on block 2, we have the phi's and the operands have not been changed, which is what I suspected. But we have more move instructions in block 1. Instead of having 3 instructions, we have now 5. Oh boy. So we move this into this. And then we have 1,000 0. What is 1,000? That's A. That's the A from the top. Oh. That's the wrong. This is the one that should be here. Let's see. Let's put some more print statements in, as always. Old place, OP place, and then we say new target is the new target. Now let's run this again. This is okay. So something is wrong because our renamer, I think, is not the hack that we assumed it would be. Yep. So the thing is, that's interesting. Okay. It doesn't have state, the renamer, so it just starts at 0. That is interesting. We need to make sure that it always gives it a new name. Can we save the renamer? What if we SSA You know what we could do? We create a new thing. Let's just do a hacky thing. And we call this the version bumper. And we say versions is this. And then we say place a lot of red here. Oh yeah, okay. Getting ahead of myself. Type annotations needed. Why? Place, import, create, place, old, P, cannot find type, register ID. What? Okay. All right, here we go. Okay. So what we want to do is we want to say we insert something, and that should say self versions entry for this, and say and modify the version v, and say if version higher than v, then v equals version. Or insert version. Okay, so now we say rename and we do the same thing. Yep, that works. So we go up here and let's say instead of the renamer, we have the version bumper. And we remove the renamer. And now we do a really stupid thing. We add another loop. All of this can be removed. And we say for ins in block instructions error. We say renamer insert ins target. Yep. And then down here, the bumper would have the state of all the old names. So if we run the tests, there you go. There you go. So the old place was 1002 and the new target is 1003. And the old place was yep, there you go. 1004. So we create new names. We create the I5 and the I6 here. That's interesting. Well, it's not interesting. It is interesting, but it's interesting and cool. So now we need to take care of this, because why do we insert two new instructions? So the phi operand in block 2, right, is the phi operand for block 1. Let's say block 1. We don't insert this. The phi operand for block 1 is this. Is 1002. And then we create a new move instruction and say 1002, which is this, into 1003. But why do we also insert this one? That's weird. Let's find out. We say printdnl block is ID. Then we say bread ID is the one we're looking at. And then we say n block is this. And we say OP is this. So we say ID, bread ID, n block, OP. Oops, no test run. Here we go. Okay, here we go. We are in block 2. The predecessor ID is 0, which is the one up top. And we say n block is 1. Why is it 1? Same thing. Same thing. The block ID counter is not increment. It's the same thing again. All right. Okay, so this is also a problem. Yep. Okay, so we get the context and, well, we get 2 blocks and we say 3. Does this work? Swap, replace. Replace is what we want. There you go. So the problem was we created a new split edge to insert. But we created an overlapping block ID for that new block. So we had a naming collision with the block IDs. All right, so far, so cool, except that we now don't have a move anymore. Aha, because why? Something panicked. Yes, okay, the block doesn't exist yet. So yeah, we need to do this edge splitting. Split edges, come on. Insert phi, remove split edges. What do we do? All right, so if we have this, all right, split edges could just be a vec of tuples, right? This is hacky, but then we say split edges, push. Yeah, we push a tuple and we say, wait a second, a split edge is a triple, is it not? Yeah, it is a triple. So we say pred ID, then new block ID, and then ID. What's wrong now? Does not live long enough? Cannot clone this? Come on, man. Try dereferencing. All right, so dereference this. So now Now we do this and we say for pred new block suck. Yep, that's what it's called. In split edges. We say func split edge. What is split edge? New block ID. New block. New ins is vec new. Pred suck. If this worked. Wow. Okay, let's run tests. Okay, let's see. Okay, we got a new block. Let's see if this is actually correct. Assert false. All right, so check this out. So block 0 is this one here, which we start out here. We have our A, right? Now in block 1, this one, we have our temp moving into our A0, that's this one. And we want this new thing inserted. So up here, this is the old version. And this now has the new thing, the new move. So this is this in bold. Then we now have a new block that sits between, it's coming from block 0, and it's going to block 2. It's called block 3. And block 2 now has 2 predecessors, 1 and 3, boom, boom. And block 3 now takes I1, which is the A from block 0 here, and moves it into a new temp location. Oh, sweet. All right, so okay, so this actually worked. Sweet. The last thing we want though is to update the operands of this phi to use this one and to use that one. And then we would be done. And we would have a bunch of shitty code that we would need to refactor and clean up. All right, so I got 15 more minutes. Moving. Call this branch Gen 5 moves. That's a great band name. Hey, Bunny in chat, and just stopping by 86. Okay, so we have this. So now, how would we update the phi operands? We do have, there you go. There you go. check this out. We could say ints replace read. And is it old and new? Yeah. This is the old one, and this is the new one. This now says, I'm sure this now says it's not mutable. There you go. This worked. The borrow checker did not throw this back in my face. What? Angel voices, bright lights. I'm like, ah. Remove this mute. Why does it say this? Ah, because I don't mute it. Okay. What? This worked. If this worked, sweet Jesus. It actually worked. Look at this. Yes. So, look at this. We started with this CFG up here. Sorry, I cannot do. We start with this. And this is roughly this, what we have in the paper here in the middle. And then we end up with this, which is roughly this. And it actually worked. It actually worked. So let's check this again, right? Let's look at our graph. And then, yeah, Connie, that is a first. I was sure, like I woke up this morning thinking I'm going to stream today and people will see me fight with the borrow checker and just give up, maybe cry live on Twitch. But here we are. Only tears of joy. Okay, let's double check. So B0, that's our graph up here, which is this one, right? It starts out with, we have one move to A. Then we have B22A, blah, blah, blah. So this is our block 1 here. Here's the temp, this is the result of binary up. Then we move that into A. Z is this. So what we want is we want 2 new move instructions and we want a completely new block here. We want to split the edge. I love that word, or that, terminology. So we want to split the edge and insert a new block between B0 and B2. And if we look at what happened is, at the end of block 1, we now have a new move from 1002 is going to move into 1003. And now the phi operand for this block, which was previously I4, is now I5. It is also, check this out, the new operand. And then we have this phi operand, which is now not pointing to this block up here, but it's pointing to this block where we insert a move. So here, this is our new shiny block 3. We have a new move from 1000, which is our original A, up here, into a new temp, or a new version of A. And check this out. That operand is also updated in here. We did it. We actually did it. This is me not believing that I actually managed to pull this off on today's stream. Whoa. Thank you, Connie. I appreciate it. I really do appreciate it. So now, you know, I need to hop off in 9 minutes. But what would we do now? We need to do actual assertions, right? We have a little helper in SSA that says assert split edge. Check this out. Yeah. Connie, me too. Apparently on stream stuff works. Can we, let's see if we can move this to our helpers. Do we import everything from the helpers? Oh yeah. All right. Then we say, okay, let's make an assertion here. We do have this, and we say assert split edge. What's the? I need to ask TJ how. I need this. Damn it. So I want to see the signature of this. It says F pred F. Then we want to have B0 should be the predecessor. The successor should be B2. And the instructions, oh boy. What should the instructions be? The instructions should be empty. Let's see if this even starts to compile. Fail to resolve undefined. What? Use of undeclared type. How is assert split edge used? Oh. Well. Where's Terminator? Define middle IR, right? Pub none. Failed to resolve. Use of What is going on? Why does this not import this one? Oh, what is this, Connie? Buff signature. Yeah, I can show. I have a key binding to show the signature. The problem is, if I have there's a diagnostics error, then that takes precedence. I can hit my key as many times as I want, and it doesn't work. Assert split edge. Okay. Why does this not resolve? Is this like a reload problem? Use of undeclared type terminator. Why? Why? Reg alloc. Now I get it. Now I get it. Because a macro is just code in the thing that uses it. So I need to import it here, terminator. Right? And then assert split edge. So now I can run the tests and see, yep. So this failed because the instruction is of course wrong. To do, make this assertion use a real instruction. But that we won't do today because I really need to hop off. And with that, I will say thank you for watching and hopefully see you next time. Bye-bye.